Hi to everyone, myself C. Ahalya, EC Department, Ravindra College of Engineering for Women. Today I would like to explain about the random process. The contents present in the random process are, the first one is the random process concept, and the second one is difference between random variable and random process, and third one is classification of random process, and the last one is deterministic and non-deterministic random process. Today I will explain all these four topics. Okay? In that, the first one is introduction to random process. First we have to know what is meant by random process. Random process is also known as the stochastic process. The other name for this one is stochastic. Okay. If you see the definition of random process, it is a function of both sample space as well as time. The sample space is indicated with S and the time is indicated with T. That's why the random process is the function of both S, T. Hence, the notation for the case of random process is x of t, s. Let us consider x is something random variable. Now I want to include it as a random process. Then that is x of t, s is the notation for the random process. Next, we will see what is the plot of a random process. Let us see, this we have plotted with respect to the x-axis time and y-axis as x of t, s. That means with respect to time t, how the random process is going to changing, now we are going to plotting. Let us consider the first one, x of t, s1. How the sample values of s1 are going to changing with respect to time, it is going to described by this plot. And the second one is x of t, s2. The sample values s2, how they are going to changing with respect to time, they are described by using this plot. So on x of t, sn. The family of all these functions is known as the sample space and the corresponding is known as the random process. In that, if you see, one of that one is known as the sample function. A single plot of a random process is known as the sample function, where that plot describes how a single sample value is going to changing with respect to time. And here the time is nothing but the continuous, hence it is a continuous random process. The family of all those functions is known as the random process. We have to know what is the difference between the random variable as well as the random process. What is the definition of random variable? The random variable is nothing but the function of the possible outcomes of an experiment. That means if x is a random experiment, if you are doing, then it is a function of the sample space S, that is x of s is known as the random variable. Whereas random process is nothing but it is a function of both the sample space S as well as the time t. Hence it is indicated as x of s, t. And the second point is, in the case of random variable, we are going to mapping all the values only to the number x, because it is a function of s only. But whereas here, it is mapped to both the corresponding x as well as the time t. That's why, in the case of random variable, if you are going to including the corresponding t, that is known as the random process. In the case of random process, if you are going to removing the t, then we are going to getting at the random variable. This is the basic difference between the random process and random variable. Next, we will see the classification of random process. Based on the nature of random variable x as well as the time t, there are four classifications are there. The first one is continuous random process. Second one is discrete random process. And third one is continuous random sequence. And the fourth one is discrete random sequence. All these classifications they have done based on the random variable nature as well as the time t. First we will see about continuous random process. In the case of continuous random process, the name itself tells that the first word will describe the nature of the random variable. Since the first word is continuous, that means the random variable x is nothing but also the continuous. Okay. So now here the x is nothing but the continuous. Then another is that is a time t. Time is also continuous because here we are having the definition that is the process. The process means t is nothing but the continuous. Finally, in the case of continuous random process, both the random variable x and t are continuous. Let us see the plot for the case of the continuous random process. As I have explained earlier, on the x-axis we are having the time, on the y-axis x of t comma s1, t comma s2, so on. Here you can see that what are the diagram we have drawn, like a random sine wave we have drawn, it is going to change it continuously. That means the time t is continuous. At the same time, the corresponding values on the y-axis, if you see here, these are also continuous, isn't it? So that's why both the random variable x as well as the time t are continuous in this case. Consider the next type of the random process is nothing but the discrete random process. In the case of discrete random process, the random variable x is discrete. See, the first word discrete is there, hence random variable x is also discrete. And the last word is nothing but process. It describes that the time t is nothing but continuous. That means in this case, random variable x is discrete and the t is nothing but the continuous. See the plot of this discrete random process. So discrete means only some specific values are there. Let us see in this figure, like example of a square waveform. If you see on the x-axis, it is a time t, it is a continuously, we are having the values say t1, t2, t1, etc. But whereas here you can see this. Here only one level is there in the sample function, say high value, other one is something low value. Let us take an example of this, maybe say 1, 0, this is also 1, 0. Only two values we are having. Those are known as the discrete. That's why the random variable is nothing but the having the discrete values only. That means it is having only 1, 0. Some specific values we are having. Hence it is known as the discrete random variable. But whereas the time t, if you see continuously we are having the time t. Isn't it? Up to this. So that's why t is nothing but the continuous. The family of all these functions is known as the discrete random process. And the third one is nothing but continuous random sequence. In the case of continuous random sequence, the nature of random variable x is continuous. Because this word continuous is there, here it is also continuous. Now x is continuous. Then what about the time t? The time t is nothing but, you can see the word here is having the sequence, then time t is nothing but the discrete. This is a plot of continuous random sequence. Now here you can see, observe the time axis t. Instead of having the continuous values, only some specific values are there like this here. Let us consider only this one we are having. Say only at this point and here, 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 so on we are having, isn't it? Only sample values we are having. That means discrete time is there. And here if you see the corresponding values what you have drawn is nothing but x is the continuous. Some continuous specific here values are there like this. Let us see here. So that's why the random variable x is nothing but continuous and time t is the discrete. Then consider the last type of random process is nothing but the discrete random sequence. In the case of discrete random sequence, the first word is discrete. That means the random variable x is discrete and the corresponding time is nothing but the discrete. Because the last word in this case is nothing but the sequence. Sequence indicates that the time t is discrete. So in the fourth case, both the random variable x as well as the time t are discrete in nature. Now we'll observe the plot of discrete random sequence. Now let us see. On the x-axis we are having the time t, and here what are the sample values are there, the specific values here we are having. See here, at the specific times only we are having the values. That's why t is nothing but discrete. And here if you see, the random variable is having either high or something low, having only two values here. Let us say 1 or 0, that's it only. Only specific values known as the discrete. That's why in this case, both the random variable x as well as the time t are discrete in nature. Okay. Having examples for the case of all these random processes, let us consider the continuous random process is there. Suppose now I am going to talking. Continuous I am going to talking in the form of a signal. With respect to time t is continuous as well as the random variable is also continuous. The speech signal is example for the continuous random process. Whereas for the case of the continuous random sequence, some digital signal can take that having only two values 1 and 0. So thus that is the best example for the case of the continuous random sequence. Then by doing the sampling process of these two, we are going to obtaining the remaining two. So this is based on nature of the random variable x as well as the t, we have classified the random process. Then once again have a glance, what is the difference between all these random processes? These are the four types of random processes. This is a specification for the random variable as well as the time. The first word here if you see, we are having continuous. That's why the random variable is also continuous. Here we are having discrete. So this is also discrete. And the next one is continuous. So this is also continuous. And the next one is discrete. This is also discrete. The first word in the type of the random process will describe the nature of the random variable. And the last word you can observe, if it is a process, process means t is continuous. So these two are continuous. And the remaining two are sequence. Sequence means then the t is nothing but the discrete. So like this, based on the nature of the random variable x and time t, we have classified like this four different types of random processes. Next, coming to the other type of random process is nothing but the deterministic process. What is meant by deterministic process? So the deterministic random process, if you see here, the word determine means we are able to find out the future values of the sample function based on the past values. Suppose past values if you know, then future values if you are able to determine, that is known as the deterministic process or deterministic random process. Let us consider an example of a sin omega naught t plus theta. So here the corresponding parameters a, omega naught, theta are the random variables. So where these we can able to determine based on the past values. Okay. Hence it is named as the deterministic random process. Other one is we are having as non-deterministic process. In the case of non-deterministic random process, the name itself tells that we are unable to detect or determine what are the future values based on the past values. You can see that here, what is the sample function value? We cannot determine or we cannot be detected from the past values. That is known as the non-deterministic. Like an example of an experiment of say tossing a coin experiment is there. Suppose I have tossed a coin. At that instant we are going to getting the outcome as say head. After 1 minute, suppose at the same conditions again I am going to tossing. You can't guess that what we are going to getting. Of course previously you are going to getting head. Next time you may get either head or tail. You can't decide, isn't it? That is example for the non-deterministic random experiment. With respect to time, how it is going to changing is described by using the non-deterministic random process. So for that type of process, whatever we want to describe, we are going to using the probability constant theory. Okay, that's the completion of the 4 topics in this session. The first topic is nothing but the introduction to random process, and second one is difference between random variable and random process, and third one is classification of random process based on random variable as well as the time, and the last one is deterministic as well as the non-deterministic random process. So thus now we have seen about the random process definition as well as the types of random process. To describe about the random process, we have to know there are some functions are there which they are describing about the random process. Those are distribution function, second one is density function, and the third one is nothing but the statistical independence of a random process. First, we will see about the distribution function. What is meant by distribution function? Generally, to describe any random variable or random process, there are some functions are there known as the probability distribution function as well as the probability density function, are shortly known as distribution as well as density functions. In that, the first one is the distribution function. Here, based on the how many random process we are going to using, we are having different types of the distribution function. In that, the first one is nothing but the first order distribution function. Here we are going to taking only one random process. Generally, the random variable is indicated as x and the corresponding random process is indicated as x of t. By including time t, we are going to getting the random process. And the distribution function is indicated with capital Fx of x. In the case of random variable. Now in that we want to add the time t. That's why the notation for the case of the first order distribution function of a random process is Fx of x1 semicolon t1 is equal to probability of x of t1 less than or equal to x1. By including time t1 specifically for the case of x of t1, here I am taking one of the random process is nothing but the x of t1. Specific time I am going to taking. Hence, it is nothing but the first order distribution function. Then coming to the second order distribution function. For the case of second order distribution function, we are going to using x of t1 as well as x of t2. At two different times t1 comma t2, we are going to defining a random process, and that's why the second order joint distribution function is defined as Fx of x1 comma x2. Now see here two random processes are there at two different times t1 comma t2. That is equal to probability of x of t1 less than or equal to x1 comma x of t2 less than or equal to x2. In the previous case only one random variable is there, so thus we have taken only one time t1, so thus we have indicated only one probability. Now here we are having the joint, hence it is named as the joint distribution function. So this is the second order distribution function, and so on can go for third order as well as fourth order also. Going for the common, that is the nth order joint distribution function. Let us define x of t1, x of t2, so on, x of tn are there, different random processes are there. They have defined the random variable with respect to time t1, t2, so on, tn are there. So the notation for the nth order joint distribution function is Fx of x1 comma x2 so on xn semicolon t1 comma t2 so on tn is equal to, this entire LHS is the notation for the nth order joint distribution function, that is equal to probability of x of t1 less than or equal to x1 comma x of t2 less than or equal to x2 so on x of tn less than or equal to xn. How many random processes at respect to times we are going to taking? The number of terms here we are going to getting. So this is about the distribution function of first order, second order as well as the nth order. It is also known as say one dimensional case, and this is nothing but the two dimensional case, and this is the n dimensional case. Then the next one is nothing but the density function. This is one more function that will describe about the random process. Again in this also we are seeing the first order, second order as well as the nth order. In the case of density function, it is indicated with small fx. Small fx of x is the notation for the density function for the case of the random variable. If that is included for the case of random process, we must start include the respective time t. Okay. In the case of random variable, you can recall that small fx of x is nothing but d by dx of capital Fx of x. Capital Fx of x is known as the distribution function and this is the density function. That means density function is equal to derivative of the distribution function. This is for the case of random variable. Now I want to extend this one to the random process. That means include time t. Based on the corresponding order, we are going for either t1 or t2, etc. Now let us consider for the case of the first order density function. First order density function means now we are going to writing the notation as small fx of x1 semicolon t1. Here I am going to taking only one random process x of t1 at the time t1 only. That is equal to, let us say here the same here differentiation, that means d by dx. Now I want the specifically only for first order, that's why this is the dx1 of fx of x1 semicolon t1. The first order density function is equal to the one-time derivative of the first order distribution function. Okay. Then coming to the second order density function. I am taking two random process x of t1 comma x of t2. That's why here the second order density function is fx of x1 comma x2 semicolon t1 comma t2. At two different times we are going to taking. One random process is at t1, other one is at t2. That is equal to, since it is the second order density function, we have to do the 2 times derivation. For that, I am going to take in the partial derivation, that instead of writing d as, we are going for dou, that is dou square by dou x1 dou x2. One is for this x1, other one is for this x2 of, this is nothing but the second order joint distribution function indicated as capital Fx of x1 comma x2 semicolon t1 comma t2. Thus finally, the second order density function is equal to the 2 times partial derivation of the second order distribution function. Then so on, if you are going for the general case, that is the nth order density function. Its notation is fx of x1 comma x2 so on xn semicolon t1 comma t2 so on tn is equal to. Now this is the notation for the nth order density function. By taking different times like t1, t2 so on tn, that should be equal to, again same differentiation, because more number of differentiations are there, I will take the partial derivative. That's why dou power n by dou x1, dou x2 so on dou xn. Here x1, x2 so on xn are there. So that's why here also we are going to getting as dou x1, dou x2 so on dou xn of, this is the nth order distribution function, that is capital Fx of x1 comma x2 so on xn semicolon t1 comma t2 so on tn. That's why finally the nth order density function is equal to the n times partial derivative of the nth order distribution function. So based on the corresponding order, this is the first order, this is second order and this is the nth order. Here we are having one time derivative and here 2 times and here it is the n times. That's the respectively first order, second order, nth order density functions. Simply, the relation between the density function and distribution function is nothing but the density function is equal to the derivative of the distribution function. Recall all of you once again the main difference between the notation of the density and distribution function. Distribution function is capital F and density function is small f. So this is about the density function as well as the distribution function. These two will describe the random process nature. Next one is statistical independence. General independence, I think you know, that means we should not depend upon others. Similarly here also, in the case of the random process, one random process should not depend upon the other. Suppose x of t1 is one random process, x of t2 is other random process. By using density function as well as distribution function, earlier we have seen that we are going to describe in the random process. Then what is the condition for the case of the statistical independence? General independence, specifically you can known as statistical independence. For the case of second order, if you see, this is a second order or two-dimensional distribution function. Capital Fx of x1 comma x2 semicolon t1 comma t2. That is a joint distribution function is equal to the, here if you see the first term, this is fx of x1 semicolon t1. Second term is fx of x2 semicolon t2. Here you can see that this is nothing but the distribution function of x of t1 and this is the distribution function of x of t2. Okay, that means the joint distribution function is equal to the product of individual distribution functions. Here it is combined, isn't it? Joint, but here we have done separately. Product of individual, that means x of t1 is not depending upon x of t2. This is the main condition for the case of the statistical independence. Not only here for the case of distribution function, even density function also. The joint density function is equal to the product of individual density functions. Instead of capital F, we can go for even small f for the case of the density functions. The last one is, this is for the case of the n-dimensional case. That means nth order joint distribution function, capital Fx of x1 comma x2 so on xn semicolon t1 comma t2 so on tn is equal to the fx of x1 semicolon t1, fx of x2 semicolon t2 and so on fx of xn semicolon tn. Product of all this. So this is nothing but the distribution function of a random process x of t1 and this is the distribution function of the random process x of t2 and this is for the case of x of tn. That means the nth order joint distribution function is equal to the product of individual distribution functions. Here we are having all the combine of all say x1, x2, so on t1 comma t2. But here we are having independently, that means separately we are having. Hence it is a condition for the case of statistical independence of nth order. Similarly, this corresponding capital F can be replaced with a small f such that nth order joint density function is equal to the product of individual density functions. So this is one more topic related to the random process.